So in the video on principal component regression, we found a way to fix the problem with ordinary squares by just regressing onto the principal component scores instead. So that was a method we called principal component regression. In this video, we're going to take a different approach to fixing these problems. So instead of minimizing the sum of squared errors, y minus x beta squared, we add a penalty term that penalizes the parameters that are too large. So we add a penalty term like this. Okay? So the norm of beta here tells us something about the size of beta, and lambda here controls the size of that penalty. Okay, so we've got a penalty parameter, and what we're going to try and do is find the betas that minimize this expression. So just note here that what happens as lambda goes to infinity? Well, as lambda goes to infinity, this part doesn't really matter. Yeah, this part is going to dominate this term. So as lambda goes to infinity, the parameters that we estimate are going to go towards 0. So they're going to shrink to 0. What happens as lambda equals 0 here? If lambda equals 0, then the parameters we estimate are just going to be the least squares estimates. Yeah? There's no difference at all. If lambda's 0, we don't have a penalty, we get ordinary squares. So what we're going to find is that using this kind of penalty term here shrinks the parameters. So these are called shrinkage methods. Now, in particular, we're just going to look at one shrinkage method called ridge regression. So ridge regression picks beta hat, let's call it beta hat ridge, to be the value of beta that minimizes the sum of squared errors plus lambda times, and we're going to specify the norm here. We've got the L2 norm. Okay, so it uses this is the sum of beta I squared, I equals 1 up to p. Yeah, the L2 norm of the parameters. So the value of beta that minimizes that, in this case, is called ridge regression. And you've probably seen this if you're an undergraduate here. You probably saw it in the second year module. Okay, and if you're an MSc student, you may or may not have seen it before. But don't worry, it's just like ordinary squares. So what you're going to see on the example sheets is that our ridge regression estimator, beta hat ridge, is equal to x transposed x plus lambda I inverse x transposed y. And what we're going to show on the example sheet, okay, so we can show that the matrix, the inverse, always exists as long as lambda is bigger than 0 here. Okay, so this ridge regression gets us around the problem of having a non-invertible matrix that we sometimes have in ordinary squares. But as we're going to discuss, there's other advantages as well. So one of the things you'll see on the example sheets is, as I say, that the ridge regression estimator is smaller than the OLS, okay, and whatever norm we choose, but let's have the 2 norm here. The effect of ridge regression, or the effect of having this penalty here, is to shrink the parameters. i.e. ridge regression shrinks the OLS. So why do we want to shrink them? We've already said why we like ridge regression, because it makes this term always invertible. But why do we like this shrinkage? Well, I put a quote from a very popular statistics textbook, and what they talk about in that book is that when we have many correlated covariates, you know, when X has many columns and some of those columns are correlated, we can sometimes find that the coefficients are kind of poorly determined. So the OLS estimator can have high variance. And the quote from the Hasty book is that a wildly large positive coefficient on one variable can be cancelled by a wildly large negative coefficient on its correlated cousin. Yeah. So if you have two correlated columns, you might find that you have a really big coefficient on this one and a really negative coefficient on this one to cancel out. And that's going to create a lot of variance in your estimators. So by imposing this size constraint on the coefficients with ridge regression, we can try and prevent this phenomenon from occurring. Okay, so there's benefits from ridge regression in terms of controlling the variance. So let's think about the fitted values, because they're easy to compare. So if we look at the fitted values, they are going to be x times beta hat ridge, which is x times x transposed x plus lambda I inverse x transposed y. Now let's substitute in our SVD. So we're going to substitute x equals u sigma v transposed. So this is going to give us u sigma v transposed, v sigma squared v transposed plus lambda I v sigma u transposed y. Now let's be a bit sneaky here. This is u sigma v transposed. Now let's think about taking this term here. So we've got v, and I want to write this as sigma squared plus lambda I v transposed, v sigma u transposed y. Now remember, v transposed is the identity. Okay, so they cancel out in here. Oh, I forgot an inverse here and here. Okay. So now when we do this, we're going to get u sigma v transposed v sigma squared plus lambda I inverse v transposed v sigma u transposed y. So these cancel, and I get left with u sigma squared plus lambda I sigma u transposed y, which if we write this out, we get the sum from I equals 1 to p. Well, I forgot minus 1. If you think about this, this is going to be the same form as we had before, ui transposed y, but the coefficients here are going to be the singular value squared over the singular value squared plus lambda. Okay, so just note this term here are all less than or equal to 1. So they are shrunk towards 0. So what we had before, if you remember, for OLS, we had the fitted value for OLS were just the sum from I equals 1 to p of ui transposed y. And for ridge regression, we had sum from I equals 1 up to k of ui transposed y. So ridge regression took this sum and truncated it. Sorry, PCR took this sum and truncated it, just took the first k terms. Ridge regression takes a different approach and it shrinks the terms. And the amount of shrinkage we get here is going to depend upon the size of the singular values and lambda. So for large singular values, sigma I large, these aren't going to shrink very much. Whereas small singular values are going to be dominated by the lambda and the denominator, they're going to shrink a lot. Okay. So we get shrinkage more in the less important directions, in the least important directions. And then just finally, as a point of interest, note that there's also a popular method called the Lasso. Okay. The Lasso estimates beta to be the value of beta that minimizes the sum of squared errors plus lambda times the L1 norm here. Okay. So instead of using the L2 norm, we minimize the L1 norm. And this gives us a very different type of shrinkage estimator, which you can read about if you like on Wikipedia or many places on the web. Okay, but it's a different type of shrinkage estimator that works very well in some higher dimensional problems, but is a bit beyond the scope of the module here.
Okay, so let's look at an example and look at how we do this in R. Now we're going to use the GLMNet package, General Linear Model Net package to do ridge regression. So this package doesn't quite solve the optimization problem we had, but a closely related one, a more general one. So the problem they solve here is that we find the value of beta that minimizes the sum of squared errors, and then lambda, penalty term, times alpha times the L1 norm squared, plus 1 minus alpha times the L2 norm squared, where we have to specify the value of alpha to use. So just note here, if we take alpha equal to 0, this term disappears, and we just get lambda times the L2 norm of beta squared. Okay, so that gives us ridge regression. So alpha equals 0 gives us ridge regression. Alpha equals 1 here cancels this term, and we just get the L1 norm of beta. That gives us what's called the Lasso. And values intermediate, so alpha between 0 and 1, balance these L1 and L2 penalties. And this gives us a method that's known as the elastic net. Now, that's not so important here. We're just going to take alpha equal to 0 to look at ridge regression. But if you want to in the course, you can do, look at other methods as well. But we then need to specify what values of lambda to use, how much to penalize big parameters. And if we don't specify it, GLMNet will pick some sensible values for us, but it's better to pick them yourself normally. So remember that large values of parameter, lambda, result in bigger penalties and so greater shrinkage of the parameters. So what I've done here, I've picked some lambda values between 10 to the 3, so 1,000, so a really big value, and 10 to the minus 4, so practically 0. And I've picked them at intervals of 0.1 between these two extremes. So I've picked an awful lot of lambdas to try here. Then, slightly annoyingly, we have to provide GLMNet with matrices. So I've said let X be the matrix that's the columns 2, 3, 4 of the Irish data set, and let Y be column 1. Then the GLMNet command just take the matrix X and Y as inputs. You specify alpha, so I said 0 here to get ridge regression, and then I passed in the lambdas I've just specified. And then what we get are parameter estimates for each possible value of lambda. So you can see that when lambda is very big here, I've plotted log lambda on the x-axis. You start with large values, and the parameters all shrink to 0. They start off at 0 here. And as lambda decreases, okay, it gets smaller, we get back to the ordinary least squares estimators. So remember that the OLS estimator of the parameters, what did we find? We found for 0.65, 0.7, and minus 0.56. So if we look here, that's what we've got here. Yeah, the values we had before. Okay, that's when we have lambda close to 0. Okay, log lambda very negative, and as lambda increases, the parameters shrink towards 0. So how do we choose lambda? Well, just as we did in PCR, in principal component regression, where we chose the number of components k, we choose lambda by finding the value which gives the lowest prediction error on some sort of test set. So again, we're going to use cross-validation here, which details don't really matter for this module, but you split the data up into test and training sets multiple times. Okay. So if we do this cv.glmnet command, it will tell us the mean squared prediction error for each different value of lambda here. And this plot will then plot it. Okay, so you can see here, when we have large values of lambda, we have quite a big error. And as lambda shrinks, the error gets smaller and smaller. And so the best error here is for very small lambdas. Okay, so very small lambdas are the ones where we get back to OLS, ordinary least squares. OLS is optimal in this problem. Okay, but in some problems, we can see the error decrease and then start to increase again as lambda gets too small. So you'll see that on the example sheets. Okay, so sometimes it does pay to have lambda, but not in this example. So the two vertical lines here show, the first one shows the value of lambda that minimizes the error. So that was at 0.0005 here. On a log scale, that's -7 something. It's just here. The first line here is the largest value of lambda that gives a prediction error within one standard deviation of the minimum. Okay, so it's kind of like the largest value of lambda you can use. It gives, statistically speaking, about the same error as the best possible value of lambda. Okay, so we normally pick one of these two for our choice of lambda. Okay, and you can access them this way from the output of the cb.glmnet command. Okay, two different ways of outputting those numbers. Okay.